And I hope my screen is now visible to everyone. All right. So I was not aware from which point I should start this talk. So what I have done is I have started it with very basic. So those of you who are not even aware with the concept of ADC, they can understand it. So I will start from that point, and then we will see up to which point we will be able to go in this 1 hour kind of discussion. So just to start, signals is something which I think most of you are aware of. Signal is nothing but variation of some information with respect to something. This something need not to be time always. For example, if you look at image is a variation of contrast with respect to position. So your function can also be with respect to position sometimes, but most of the time we see it is with respect to time. Okay. So signal you can always define using a function, and now you have two parameters. One is independent parameter and one is dependent parameter. So independent parameter, for example, let's say if you are looking for temperature as a function of time, then time is the independent parameter and temperature becomes a dependent parameter. So now most of these signals, because they are with respect to time and there are two parameters, so these parameters can be observed either continuous manner or you can observe them at certain point of time, right? So if you observe them in continuous manner, then these are known as continuous version of signal. So for example, if you are observing them across all the time, then you will call them as continuous time signal, okay? And if you are observing them at certain time points, then you will call them as discrete time signal, because you are not observing them across all time points. This discretization need not to be just in time. Let's say if you are looking for information, let's say amplitude of a signal, then amplitude also can exist either in a continuous way, or you can say that only certain amplitude are permissible in a signal. So again, amplitude can also be like continuous amplitude and discrete amplitude. So now because there are two parameters, each of these parameters can exist in two ways. So there are four possible scenarios. Like I have shown this through this table. So one scenario is continuous time, continuous amplitude signal. These signals are the one which exist in the real world. So if you look for anything in the real world, that is essentially continuous time because it exists at all time points and it can take values in a continuous way, right? Obviously, until and unless you are not looking for the quantum or quantization effect, right? So at that level, maybe some discretization is there, but otherwise it looks as if everything is continuous. So these kind of signals are called as analog signals. The reason why they are called analog is analog word has come from analogous. So these are the signal which are analogous to the real world signal, and from the analogous we have picked up the term analog. Okay. Now another category which is very which occurs more frequently is the complete opposite version of it, where the time is also discretized and the amplitude is also discretized, and these kind of signals are known as digital signal. So frankly speaking, digital signal doesn't exist in real world. This is just a mathematical representation or a mapping. Although you may hear that many systems are digital, so the meaning of that is the processing which we are worrying about is happening according to the representation which we call digital. But any signal which you are observing in the real world is actually an analog signal. It's not a digital signal. Okay. In between, there are two other categories. They are mostly for transition, because let's say if you want to make analog signal into a digital signal, then first you have to discretize one of the parameter, let's say either time or amplitude, then you will do the other. Doing it all together may be slightly difficult. So you can take whatever way you feel. For example, you either can go by this way or you can go by other way. In most of the cases, you will find the preferred way is this, and there is a reason for that. I will describe that reason in the coming slide. Okay. So these classifications where signal is discrete time but amplitude is continuous is known as discrete time signal because we have just discretized the time. The other counterpart of it is very less frequently used, but here the time is continuous. However, the amplitude is discrete. So it resembles more with a digital signal. That's why people also call it as continuous time digital signal because the time is still continuous in this case. Okay. So let's first understand that if real signals are analog or real world signals are analog, why at all we are talking about other representation. So the problem with analog signal is that it is sensitive to noise. So for example, let's say consider a signal which is this nice sine wave, and because in this signal all amplitude are distinct information. So even if a slight disturbance comes, noise in the neighborhood, the amplitude changes. That means information has changed. So now your signal has got corrupted. So that is the problem with analog signal. Although they can exist in the real world, they can be directly processed, but they are very sensitive to noise. This is one problem. There is another problem which I will try to highlight in this slide. So let's think about there is some analog signal and you want to process this signal, and for processing you sometimes want to store it so that you can manipulate the information. So now let's consider even I am not trying to store the complete signal, I am just trying to store a part of it. Even in this part, if we think if the signal is continuous time, that means there are infinite time points possible. And now if you want to store the information of all these time points, then practically you need infinite memory. Because if let's say you are using some memory like flip-flop or register, right? So at every time point you want to store the information. And in a continuous signal, between 2 points, there can be infinite time points, right? So you understand this problem. Obviously, there can be one easy solution for this problem, that instead of digital memory, you use analog memory. Do any of you know any example of analog memory? Like digital memory is like flip-flop, register, but do anyone know what is analog memory? I am pretty sure that all of you have seen that. All of you must have used it also, but maybe you are not aware of it. Any of you? What is the example of analog memory? Can be said, but there is a much simpler example. Not even transistor, even further simpler. Yeah. Yes, please. Yeah, you are still going into complex domain. Like magnetic tape also, capacitor, yes. So capacitor is an example, right? Even inductor is an example. So in capacitor, you can store the information as a voltage, and in inductor, you can store the information in terms of current, right? So these are example of analog memory, and once you have this, you can store with infinite precision. But the point is, as we already discussed, these memories are sensitive to noise, right? Because these are analog memories. So analog, anything which is analog has a problem that it is sensitive to noise, because all time points are essentially different information. Okay. So, but you know, this infinite time points problem is not so severe, thanks to the people who have earlier predicted, like there is a theorem which is known as Nyquist sampling theorem, and this theorem says that if the information which you are processing is band limited means only frequency component can exist till certain frequency, then you need not to store all time points. You can just sample the points following the Nyquist sampling criteria, which says that if your speed is maximum speed is f, you need to sample only at 2f. Even if you sample at 2f, you should not be losing any information. So that means within this time duration, there can be fixed number of time points. For example, I have mentioned here, right? So you can follow this criteria, and now you can say I need not to store all the time points. I will just store fixed number of time points following the Nyquist criteria, and then I am done. So at least problem got solved till certain extent. The next thing is, now when I want to store these information, because they can take any values, so obviously I need analog memory, which I already discussed with you is sensitive to noise. So another idea is, instead of storing them in analog format, you store them in digital format. So digital format means you can map them to certain discrete number of levels. For example, the simplest representation is a 1-bit representation where I will either store it as like some plus VDD or minus VDD. Now, obviously, when you map this, you will introduce some error because the actual value and this mapped value are not same. But unfortunately, we cannot do anything here. We were fortunate in Nyquist sampling criteria, that was lossless phenomena. Here, you make a loss and you say that this loss is whatever error I am introducing here is the error in quantization. This phenomena is known as quantization, where you are mapping continuous amplitude value to a discrete amplitude level. Okay. Now the whole job of ADC designer is to ensure how this quantization noise can be minimized, right? So if you want to be a good ADC designer, you should learn the techniques through which you can minimize this. Obviously, one approach is I can have many more levels. If you have many more levels, then you can map the analog value to the closest level which you are encountering, right? So this way you can help yourself. We will see how these things are done, okay? So just to summarize, like if you want to convert an analog signal into digital signal, you need 2 steps. In first step, you do the discretization of time, and in the second step, you do the discretization of amplitude. The discretization of time is known as sampling, while the discretization of amplitude is known as quantization. As we have already discussed, the sampling can be made lossless process, while the quantization is a lossy process. Okay. Now, one question somebody can ask: the order, should it be kept in this way, like first sampling and then quantization, or can it be reversed? Because ultimately you have to discretize both the parameters. So why it is important that I should first discretize the time and then amplitude, not vice versa? So the answer to that question is, suppose you have this sine wave, and let's say I am doing the amplitude discretization first. So let's say I am trying to map this with let's say 2 bits or 1-bit signal. So in 1-bit signal, this will look something like this, right? Now, and we all agree that during quantization we encounter some error. So that is okay. Now let's focus on sampling. So earlier when you had this sine wave signal, what was the maximum frequency? Whatever frequency sine wave was having. So you can always choose sampling rate twice of that. Now once you have discretized the amplitude, in this new waveform, what is the maximum frequency content? Is it still the same frequency f, or is it much higher than that? What do you think? Any of you? Yes? Why it is same? Isn't it a square wave? Do you know about the Fourier component of a square wave? Shouldn't this be like many higher components are there? Because this is a square wave theory, right? You have sharp transitions and you have not yet discretized the time. So you cannot lose any time points, right? This is still a continuous time signal where you can see sharp transitions. So it's clearly a square wave which can have all the harmonic leading to infinity. So now ideally your bandwidth is infinite. So now if you want to make sampling as a lossless process, what should be your sampling rate? It should be infinity, right? So if you make any sampling rate, any frequency other than infinity or lesser than infinity, you are going to have losses because some component are going to alias and these will result into error, right? So this is just the information why you should always do sampling and then quantization, not the other way around. Because if you do other way around, you will encounter the losses in both the process, right? And that's not a smart choice. Okay, so just to summarize, this whole business, see, sampling is anyway lossless. So let's, the mathematical representation just a gain of 1. However, quantization, because it's a lossy process, so you can represent it using this mathematical equation where V of n is your input to the quantizer, E of n is the error which you encountered during quantization, and this VQN is essentially your quantized output. So this is a simple representation, although this is a very approximate representation. In actual, because when you are doing this, you are clearly saying that my input is completely uncorrelated with the quantization noise, which is actually not the case. Because if you know the input, you can very well predict the quantization noise. So it's not completely uncorrelated, but you know, most of the time as an engineer, we don't look for the exact thing. We look for the simplest thing which gives the accurate representation. So it may not be like the completely accurate, but as long as the effort and accuracy both are like maximized, right? So effort should be minimum and accuracy should be maximum. The moment that can happen, then you go ahead with that, and apparently this equation works well for that reason. So we don't worry much about that. So this is just the simple representation diagram. You are doing first sampling and then you are doing quantization. Sampling can always be thought of, you are having a switch and then you close this switch whenever you want to sample, and then you open this switch so that now you have held the value which you have sampled and you are no longer affected by the input any after that. Then the quantization can be thought of as whatever this sample signal is coming, I am adding some error to that and then I am getting a quantized output. Okay. Now sampling, as I already told, can be thought of just as using a switch you can estimate. The quantization is mostly done using a block known as comparator. So comparator is nothing but it's a block where you have some input and you compare this input maybe with some reference signal, and whenever the input is, let's say, higher than reference signal, you may give output as 1. Other way around, you give output as 0, right? So this comparator is the fundamental building block of designing ADC, right? Now let's focus how you can design a comparator. So one way of designing comparator is you take an amplifier with a very high gain, right? So let's say think about you have input signal. Let's first fix reference as 0 and input signal let's consider is 0.1. And in this case, the output levels are either +1 or -1. Okay. So now what you do is you take input signal, just see what is the difference, that is 0.1 right now. And now if you take an amplifier with a gain of 100, what should be output? Input is 0.1, gain is 100, output should be 10. But generally in an amplifier, the output gets saturated to the power supply. So let's say if its power supply is ±1, let's say VDD is +1 and ground pin you have connected to -1 or the negative supply you have connected to -1, then the output in this case will be clipped at +1. So this is working like a comparator. Similarly, if let's say the input goes to minus 0.1, then your actual input is minus 0.1, multiplied by 100, it should be minus 10, but again your negative supply is minus 1, so it will get clipped at minus 1. So this is working perfectly like a comparator. However, there is a one problem. The problem is, what if my input is not 0.1, rather it is 0.001? Now in this case, if your gain is still 100, then 0.001 into 100 is how much? It's 0.1. And 0.1 is lesser than your supply voltage. So now you are neither at +1 nor at -1, you are somewhere in between. And this effect is known as metastability. So in a comparator, when you are neither in one of the valid state, you call your comparator output is in metastable state. And this is not good because your digital domain doesn't understand this. Digital domain only understands +1 and -1. Now, how can you solve that? One can say you choose an amplifier whose gain is sufficiently high. But the problem is, even if I choose a higher gain, you can always find the input which is so small that for that gain, the output will be metastable. So one way is like you can always make a engineering choice. You can say, okay, I am going to work within this range only. But principally, this idea is not good because in this idea, when my signal is small, even if I wait for a long time, my output is going to remain in metastability. It is not going to come out of it. So because of this, people have come up with another architecture of comparator. This architecture is known as regenerative latch. So in this architecture, you have, let's say, one transconductor block. So those of you who are not familiar with the transconductor block, this can be thought of as like voltage controlled current source. So you have some input voltage and your output current will be proportional to the input voltage. Okay. So now what is going to happen in this block? Actually, you have a positive feedback. And because of this positive feedback, this one structure, if you think, is essentially one integrator. One integrator means in Laplace domain, this is like first order differential equation. Now when you have two such blocks, it's like a second order differential equation. And when you solve this second order differential equation, you get this solution. I'm not going to go how to solve this. I am assuming you already know how to solve a second order differential equation. What I am going to focus on the solution of this. If you look at this solution, there is one interesting thing. You have two terms. One is exponentially increasing term. The other is exponentially decaying term. So the exponentially decaying term, with time, it will die out. So we need not to worry about that. However, the exponentially increasing term, as the time will progress, it will keep on increasing. And anything which will keep on increasing, if you know the circuit design, finally it will saturate either at plus VDD or at minus VDD. So now in this case, you start with some initial condition, and now depending on that initial condition, if that initial condition is positive, you are going to saturate at plus VDD. If that initial condition is negative, you are going to saturate on minus VDD. But the good thing here is, even if your signal is small, you will take more time, but at some time point, you will saturate at plus VDD. Not like previous case. In previous case, even if you wait for infinite time, you are stuck in between the two states, right? So this latch is better in a way because if you allow more time, there is a chance that metastability can come out to a valid state, right? So this latch is more frequently used. How to realize these transconductor? Not very difficult. In fact, if you take just CMOS inverter and put them back to back, they actually realize this structure only because these two inverter then behave like a transconductor, and that is the reason whenever you look at flip-flop design, mostly you will find there will be a component where two inverters will be connected in back-to-back configuration. So that is essentially this latch only. Okay. So this latch is very useful. Okay. Now, obviously this is just the quantization, but to add the sampling part of it, you can add these switches so that input you can sample, and whatever this input which gets sampled over these caps, that act like an initial condition for your latch, and then latch takes from this point, and then it starts either taking it to plus VDD or to minus VDD, depending upon the initial sign of this sampled voltage, whatever you have sampled, and that's how you realize 1-bit comparator, or you can also call it as a 1-bit ADC, because you have already digitized the signal. So when you go in ADC design, there are variety of ADC available. All these ADCs are classified in two categories. One category is known as Nyquist rate converter. What is the meaning of Nyquist rate? As I earlier mentioned, the sampling rate criteria tells you that your sampling rate should be twice of your bandwidth or maximum frequency component. So if you are following this criteria very exactly, then your ADC will be known as Nyquist rate converter. But people ask the question that this criteria says you should never be below this rate, but what if I operate my ADC much higher than sampling rate? So apparently you get some benefit when you operate them at much higher rate than the Nyquist rate, and such kind classification is known as oversampled ADC. In fact, these ADC trade sampling rate for accuracy. So this idea I always explain through this example. Suppose you have, let's say, a 10 rupee note, okay, and you want to buy a coffee, and let's say coffee comes in 7 rupees. So now you have only two options. Either you can give this 10 rupee note to the guy, and that guy also have only 10 rupee currency, okay, or in that segment. So now when you pay him, either you won't pay and then there is an error of 7 rupees, or if you pay, then there is an error of 3 rupees, right? Now the question is, you want to minimize this error. So how can you minimize? What you can do is, you can go to that guy again on next day. So you go buy a coffee, next day also you bought a coffee, and let's say next day also you gave him another 10 rupees, and third day when you went, you say, hey, you already have 6 rupee extra now. So today I will not pay you, but you give me coffee. So now he gives you coffee, and what is the error now? The error is 1 rupee only. So you see the error has come back. So now if you keep on doing this for long, what you will find, your error is always bounded between 0 to 10. But because you have bought so many coffee, so when you see the error per coffee, that goes tremendously down, right? Because now you are dividing that 0 to 10 with number of cup of coffee you have taken. So this is the same idea you do in oversampling. So oversampling means I am observing the event again and again within the same time, and then I am going to average all this, and so that error can be minimized. So what I am trying to say, you can take a very crude ADC, let's say 1-bit ADC or just a comparator, but by observing again and again and again and again, and then averaging it out, you can actually minimize the error, because error is kind of uncorrelated while the signal is always correlated, right? So this helps. Okay, so these ADCs are known as oversampled ADC, and in fact, when I started my PhD, that was my specialization. So I will skip these slides. Rather, I will directly go to the oversampled ADC. So you can understand oversampled ADC phenomena more. Like I explained you some part of it. Another explanation is here. When you look at Nyquist rate ADC, if the sampling rate is Fs, your frequency component can only exist till half of it, which is Fs by 2. So if you assume your quantization noise to be wide, then it will be spreaded between 0 to Fs by 2 uniformly. Now let's say if I take a sampling rate double of it, okay, now my frequency component will exist again the double of this range. So now I am distributing the same noise but in double the frequency. So my height will come down by a factor of 2, right? Because the noise is still the same. You still have 1-bit ADC, but now you are distributing the noise in more frequency range. So your spectral density will go down, right? But now let's say if my bandwidth is still the same, then I can say I only care about the noise which is coming within my bandwidth. I don't care what comes outside. So I can, after this, I can put a brick wall filter and I can filter out the noise, which is not coming in my bandwidth. So this way, you can effectively reduce the quantization noise, which is appearing within your bandwidth, right? So this idea is known as the benefit due to oversampling. But now the question is, here you are pressing this uniformly and spreading it in more range. But when I have to spread it in more range, why do it uniformly? Why not do it like this? You understand? So within my bandwidth, I should try to suppress it a lot. Outside, I don't care. So it's like you have a lot of garbage in your home. How does it matter if I throw it to the neighbor? Your house will be clean, right? Is it a good practice? Yes or no? As a designer, yes. As a good citizen, no, right? You should not do that. But yes, as a designer, you want to minimize the noise within your bandwidth, so you can do that, right? So how to do that? Like now see, the thing is, I have some noise, and how I want to profile it? I want to have less component at low frequency and more component at high frequency. So what is this operation? Can somebody tell? When you are profiling with respect to frequency, what this operation is known as? When you have different gain for different frequencies, which block does this? So those of you who don't know, this phenomena is known as filtering. So filtering is providing different gains to different frequency components, right? And what kind of filtering is this? Like there are various kind of filtering. Low pass filter, high pass filter, band pass filter. What filtering is this? Where you are giving very less gain at low frequency and very high gain at high frequency. This is a high pass filter. So basically, if I have a quantization noise, and if I process this quantization noise through a high pass filter, then I should get this kind of noise profile, isn't it? But now the question is, can I do that? Like let's say I have a ADC. At the output of ADC, I put a high pass filter, and then I claim that the noise within my bandwidth has gone down significantly. So do you think it's a good design? Like, did I solve the problem? Like, did I manage to have a very little noise in my bandwidth? What is the problem here? Any of you? See, noise has reduced, no doubt about that, because you have put a high pass filter, so within your bandwidth noise has gone down. But what about signal? If you are like, if you have a ADC, and at the output of ADC you are putting this filter, so your signal is also passing through this filter, right? So your whatever factor noise has gone down, the signal also goes down by the same factor. So does it make sense when both the things are going down by the same factor? It doesn't make sense, right? Then I am not doing anything good. So now I will tell you one interesting thing. So I will do things slightly differently. So let's say the quantizer I am modeling using the equation I have shown you earlier. Let's say you have some signal, input signal, and in quantizer you basically add a noise which you call E, right? And here signal is coming, and then you are getting your output which you can call as V. Now the only thing I am claiming is, if I put a high pass filter here, both signal and noise will get attenuated by the same factor, so I am not improving anything. Now let's consider a case where instead of applying this input directly, I actually insert a block in between, right? This I can always do. Now what I do is, I take this output, I feed it back in a negative feedback fashion. So basically, there is this minus sign. And here I am applying the input. Okay? So now this system is a linear system, because I am assuming that everything is linear within this system, right? In fact, if L is linear, so this always is fine. Now, if this is a linear system, it has two inputs. One input is U another input is E. Okay, and there is only one output. So once you have linear system, you can apply the superposition. Superposition means you can consider one input at a time. You can find out the output, and the total output will be sum of these two output which you are considering one input at a time, right? So if I do that, then when I only consider U, my output V should be equal to, can somebody tell what is my forward path gain here? L. So and what is loop gain? Loop gain is also L because feedback factor is 1. So it should be L upon 1 plus L into U. Okay? And when I consider E, what is the forward path gain? From E to V? From E to V, what is the forward path gain? So this is the forward path, E to V. Is there anything coming? So what is the gain? 1. 1. And the loop gain is still L. So this will be 1 upon 1 plus L into E. Okay. Now let's consider a situation where I take a component L such that from 0 to my bandwidth, it has very high gain. While beyond my bandwidth, its gain drop to 0. Okay, consider this block. So now let's focus what happens within my bandwidth to the signal and noise. So let's first consider signal. So signal part is U. So if L within my bandwidth is very high, so what will happen to L upon 1 plus L? If L is very high compared to 1, it will be approximately 1. So my signal comes as it is, or basically I can say signal gain is 1. What happens to my noise if L is very high within my bandwidth? It will be almost 0, right? So noise is almost 0. Now let's focus outside my bandwidth, right? So this is outside my bandwidth and I put an arrow just to signify that. So now let's focus on signal part. So outside my bandwidth, L is very low, right? It can be also considered to be, I think somebody has switched on mic. Can you please switch it off? Okay. So outside my bandwidth, L is very low, almost 0. So then what will be L upon 1 plus L? 0. So, but do I really care if my signal gain becomes 0 outside my bandwidth? I don't care. Anyway, signal is not there. What happens to the noise? 1 upon 1 plus L, that means it will be close to 1. It's okay. Outside my bandwidth, I don't even care what noise will be, right? So my focus is within my bandwidth. So within my bandwidth, now I have a signal gain as 1. So signal is coming as it is. But what happens to my noise? Noise has gone down to 0. Obviously, this is a very hypothetical situation because getting a brick wall filter is not so easy. You don't get that ideally, but you can approximate it, right? You get a filter. So what that means is it will not be 0, but it can be minimized to a large extent depending upon what order of filter you are going to take. But this is the idea, right? So in fact, this block where first you kind of take a difference of the input and the feedback, right? So difference operation is generally also called as delta because this is you are finding the difference of delta. And to realize this brick wall kind of filter, you mostly do some integrator. So integrator is more like a sigma. So that's why this block is also known as delta sigma. And because its output resembles like a modulated output, so you call this block as a delta sigma modulator. Sometimes people change the term. They also call it as sigma delta modulator, but both are same. It is just the nomenclature. So this block is very popular, and in fact, this is one of the example of oversampled ADC. And now I think I have already explained you how it is minimizing the quantization noise within your bandwidth. Okay. So this is something on which I have done most of my PhD. So I don't have much time, but I will try to just give you a glimpse what kind of problem I have tackled during my PhD. So for example, in one case, we wanted to design a ADC for the wireless transceiver application, where the bandwidth requirement was in the range of tens of megahertz and dynamic range we wanted is around 70 dB. So we selected this delta sigma modulator, and in fact in this delta sigma modulator also, there are two possibilities that I told you that sampling has to be done before quantization, but you can do that either here or even before filter, because quantization is happening here. So this and this, both are like you are doing it before quantization, but that changes the nature of loop filter. If you do it upfront, the loop filter will be realized in discrete time domain. If you do it after the filter, the loop filter will be realized in continuous time domain. So apparently they also give some benefit over the others. So one version where loop filter is continuous time domain is known as continuous time delta sigma modulator, and the version where loop filter is in discrete time domain is known as discrete time delta sigma modulator. So in this version, we have selected a continuous time delta sigma modulator because it has some benefit, like it is easier to drive a continuous time signal. It also provides some inherent anti-aliasing feature because the loop filter is still in continuous time domain. So some filtering is given before the switch is coming so that aliasing can be relieved. And also it relaxes the gain and bandwidth requirement of the op-amp. So now I will come to the problem which we faced. So the problem was like this. We have input signal which was like this, and the feedback was like the DAC we were using is a single bit DAC because our ADC output which we are using in the loop is a single bit ADC. So single bit ADC output is like swinging rail to rail, right? It has only two levels. So because of that, the difference of the two signals will look something like this, right? So basically in this signal, and especially if this ADC we are operating at very high speed. So essentially you have very high speed jumping signal which is jumping rail to rail. Now this kind of signal is a problem because your virtual ground of the op-amp will start swinging with the same rate, and if your feedback doesn't come within time, then you will see these fluctuations because so basically what I am saying is your op-amp has to be very fast. As soon as this signal changes, the op-amp has to immediately supply that current, and then only due to negative feedback, your virtual ground node may remain intact. Otherwise, if let's say op-amp is slow, then you will see these fluctuations happening. Now at high speed, it is very difficult to design op-amp with a very high speed because you have some UGB of the op-amp. So now let's say if I start operating very close to the UGB and even let's say beyond UGB, then this node swings like crazy. And if this node swings like a crazy, the problem is your amplifier, which ideally you think like a linear amplifier, but the moment your signal swing becomes large, it will start showing non-linearity because your transistor is ultimately a non-linear device. So only when you operate in a small signal range, it can give you a linear output, but the moment you go beyond that range, it will inject a lot of non-linearity. So now because of that, a lot of non-linear currents are getting injected in your output and your output was becoming non-linear. So this was a problem. So this is a problem, but how to address that? So we thought one way of addressing it is, what if op-amp need not to supply that current? What if that current can be brought from somewhere else? Because if current can be brought from somewhere else, then the current is not needed from the op-amp, your job is done. So how can you do that? So what we did is, we made a replica of this and connected the signal in such a way that whenever this side demands a current, this side exactly supplies the same amount of current. Okay. Now one can argue when all the things are being supplied by this, what is the need of op-amp? You can even take away the op-amp because now op-amp is not doing anything, it is not even supplying the current. So actually still op-amp is doing a very crucial job, that is, it is maintaining the virtual ground. If you remove the op-amp, that node doesn't have the virtual ground. The only thing it is doing is, it is relaxing the requirement that at what speed the output should come. The op-amp can relax, like op-amp need not to supply or respond immediately. In fact, op-amp need not to respond at all. The current has been taken care with somewhere else. It just maintains the virtual ground. And this was a very nice idea. Because of this, I will show you some simulation. In fact, in our modulator, we used this assistance. And yeah, this is one simulation where I am comparing the performance. So here I am showing you the result without assistant and with assistance. And obviously when I am doing assistance, I have to incorporate some additional circuitry, and this additional circuitry is having some extra power. So in order to be fair, what I have done is, I have increased the power of op-amp in the case when it was not having the assistance, so that it can be a fair comparison. In the two cases, the power dissipation is exactly same. But still we can see our third harmonic has gone down by a factor of 16 dB. And that shows the promise of this technique, because now in this case, your virtual ground node is not swinging much. And if it is not swinging much, you are not injecting the nonlinear current, and you are kind of relaxed, right? So we actually realized this ADC, and the sampling rate of this ADC was around 1 gigasample per second. This work was done way back, I think somewhere in 2011. So in fact, you see the performance around that time, whatever ADCs was available, it was having a quite good performance at that time. After that, we have even designed several other ADC which was much better than this, but this is just a fundamental concept which I wanted to explain. Do we have some more time? Okay. So then I will introduce another interesting thing. See, designing ADC is one thing, but characterizing or doing a measurement is also another interesting thing. Because sometimes it happens you can design a very nice ADC, but due to limitation of measurement instrument, you are limited or you cannot validate that performance. So let's say when we want to characterize the high-speed ADC, how it works. So let's say, for example, I have designed a very high-speed modulator, and now I want to characterize it. So the general setup is like this. You take that ADC chip, you mount it on a PCB board, and then you apply your input signal and clock, and then the output data you want to grab and take it to computer, so that you can compute its FFT and you can figure out its spectrum. The only problem is how to capture such a high speed data, because for capturing high speed data you need a high speed instrument as well. So what is the problem with high speed instrument? For example, let's say if my ADC is operating at 4 gig, I need a logic analyzer which also should operate at 4 gig, and it's costly, right? It's not so cheap. Like 4 gig logic analyzer may come in like maybe 30-40 lakh. So it's not very low cost. So you have several other choices. For example, what you can do is you can deserialize this high-speed data into several low-speed bit streams. So basically dividing it into several multiple lines at a low rate. Now the problem is in packaging you need multiple pins, and if this output is swinging from rail to rail, then there will be a lot of ground and supply bounds, and because of that, a lot of noise, digital noise will come, and this creates unnecessary hurdle. So to tackle that, sometimes you can go for differential signaling, where the differential signaling can reduce the noise, but that increases your pin number to further twice. And see, increasing pin number is also not so easy. Like package has a limited number of pins, so this also is a problematic solution. And also sometimes the problem is this low voltage differential output is not supported by many instruments. So outside you have to have something which converts these logic back to the CMOS level, so that you can interface it to the instrument. So a lot of additional things are coming. One easier solution is that you can use a block known as decimator, which basically filters out anything beyond your bandwidth and gives you only the the output data rate at your Nyquist rate, because this is anyway a oversampled ADC. So Nyquist rate will be much lower. However, the problem with this approach is, now because this decimator is also a high-speed design, so the problem can come in modulator and also in decimator. Now once I grab the output, I am not sure whether the problem is in decimator or in modulator. So how to validate that? So another approach which we found easier is, you just take a 1-bit output, make it differential signal, and grab it using an oscilloscope, because in oscilloscope you can even also see the transition. But again, that problem that oscilloscope cost also increases as the frequency increases is still there, right? So we have to do something to that. So I will tell you one real story. So we wanted to characterize one ADC which was designed for, let's say, 4.4 or basically at 4 gig sampling rate. So when 4 gig sampling rate is there, if you look at the bandwidth of the data rate, it is around 2 gig. And the problem was the instrument which was available in our lab was also having its cutoff exactly around 2 gig. And now the problem was, when let's say when we were operating the ADC at 3 gig, our eye was widely open. You can see like the instrument is working correctly, because the effective bandwidth is still 1.5 gig. As we increased to 3.6 gig, eye started becoming close. And as we approach to 4 gig, you can see eye is almost close. So eye is basically the separation in this 0 and 1. Because if eye becomes close, I cannot differentiate between 0 and 1. So this is a problem, because now it may happen that some of the decisions which are actually 0 may be interpreted as 1, right? So that's a problem. And in fact, how this translates into the spectrum. So for example, let's say this is a clean spectrum. And when we were measuring the spectrum of this ADC, we were finding that noise floor is significantly high. And we are not sure whether this is due to our bad design or whether this is due to the limitation of the instrument. Okay? So to address this, what we thought is, see, the problem is happening is because we are transmitting the high-speed signal. So if somehow, let's say we can intentionally reduce the speed, then it may happen that we can get benefited. But how can you reduce the speed? Because the signal is coming at a higher speed. So one solution is, let's say you introduce some filter. For example, let's say if I take a 2-step FIR filter 1 plus Z inverse, then I am basically doing a low pass filtering where I am reducing the high frequency component and increasing the low frequency part of it. The problem with this approach is it introduced something known as ISI, which is like inter-symbol interference. Now the information from your one symbol has gone into the other symbol also, because see, earlier you were like doing this kind of switching. The moment you have done low pass filtering, you do something like this. So one information basically encroach into the other timing window also. But the thing is, if I exactly know this filter, I know how much ISI is being introduced. So then I can undo the effect of this ISI after capturing the data. So let me introduce this ISI, let me reduce this bandwidth, let me transmit this signal, and let me capture it successfully. Once I will capture it, then I will undo this effect, and then I will grab the correct data. So this was the idea. And in fact, this idea is not new. This idea is very well-known phenomena, but not in circuit community. It was a well-known phenomena in communication domain, where people call this as duo-binary coding. So duo-binary coding is a very well-known phenomena, and in fact, because of this, we saved some of the effort, because this is how your initial idea should look like. Basically, you are doing this one-tap filtering, 1 plus Z inverse, and then you will transmit this at the receiver. In order to undo this, you have to do a IIR filter, right? But in communication domain, people have realized that doing this IIR this way can result in propagation of error. So they come up with a different approach. They suggest that you swap these blocks slightly. In fact, you move this 1 plus G inverse later, bring this feedback thing before, and this they call as pre-coding. So they have already, like, this is some knowledge which I am already directly copying. I am not doing anything new. So if you do this way, your errors doesn't get propagate. So we directly use this idea because this is a well-known information. So now this is the way my signal chain looks. This is my modulator output. I am doing pre-coding, then I am doing FIR filtering, and then I am transmitting it, and my decision rule. So apparently the decision rule is very easy in this case. So if your bit is 0 and 1, what you first do is you convert it into a bipolar, -1 and 1, and then when you do 1 plus Z inverse, it either becomes -2 or 0 or 2. So basically you have 3 levels. And what we found is the decoding is very straightforward. If you have these two extreme levels, they correspond to one level, and if you have this middle level, that correspond to another level. So this is a mathematical mapping which you, if you look at the equation, you can get to know this. Okay? I will show you what we have done in circuits, and in fact, I will tell you one interesting thing here. Sometimes as a researcher, when you try to do something, that may be your intention, but sometimes the nature is favoring you, and they will give you something in addition to it which you have not even expected. That happened in this case. So in this case, obviously one thing was that we wanted to reduce this high frequency content. So for that, we were doing this 1 plus Z inverse. And when we do 1 plus Z inverse, the high frequency content has gone down. So I have a filtering. But due to this pre-coding, what was happening is there was some randomization, and because of that, the signal strength in my input, that has gone down. And this is a very good thing. Why it is a good thing? Because in a high-speed package, when you are transmitting the information, let's say here, so sometimes if it is a high-speed data, the things gets coupled to other pins also, like clock and references. Some of these switching will get coupled to them. Now, if the strength of your signal has gone down, this coupling also reduces. So this is something which we have not expected, but because we are using that chain where some randomization is happening, so this we got something which came like just a benefit or a free thing, and you can clearly see the signal strength has gone down because there is some randomization. Okay, and in fact this idea was not very heavy on our design and area effort, because this was the silicon of the old modulator, and the part which we have introduced is this small part. So this is that additional filter which we have realized. So you can see it is actually a very small portion of the whole modulator, but then I will show you the benefit which we got through this. So this was our conventional I. When we did this technique, obviously in this technique, instead of 2 levels, I have 3 levels. But now you can see at this point, you have clear separation between the levels, right? You can see out of these 3 levels, if my decision is being done at this time point, I can clearly see all these 3 time points. And in fact, I was able to characterize my ADC till 4.4 gig, which was earlier not even possible. This we can look into the spectrum which was obtained from the captured data. So this was the old spectrum, and once we designed this idea, and we again characterized using the same platform, same instrument, we were able to get this performance. So this actually tells that the performance was limited by the instrument, not by the design. Right? Design must be doing the same, but due to the limitation or limited bandwidth of the instrument, we were not able to characterize it. Right? So this I was just telling you that sometimes your innovation need not to be at the design level. Your innovation can come at the characterization level also. Right? So you can innovate at any level. Doesn't matter. As long as you are giving benefit overall, then it is value. Right? So in fact, this was the idea which I think initially during introduction somebody talked about one of my paper which got Best Student Paper Award. So this was the idea which got the Best Student Paper Award in International Symposium on Circuit and System Conference, and it's like very highly reputed conference in circuit domain. So you can see in this idea, like our effort was only limited at characterization, but still it was valued because overall it was benefiting a lot. Earlier what was limited, due to this idea we were able to prove that the performance is limited not due to design but due to characterization. So just to summarize, I think I hope that I have given you some introduction of ADC. Maybe after this you will be able to appreciate what is ADC, how it works, what is delta sigma modulator. I'm not sure how much like accurately or how much clearly I was able to talk about it. But during this talk, I have talked about one design where we have demonstrated ADC, and also we have talked about the characterization. So I think I will end my talk at this point. If you have any query or questions, then I'm open to it. Yeah.
Any questions?
Yeah, hi. Okay. 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 This like whatever spec you have talked about, that's a very straightforward design. So like if you want, I can direct you. You just drop me an email and I will direct you to some of the literature. I'm not sure if this is the right forum where I should be telling the solution, but because that is a very straightforward solution, right? So even a 1-bit modulator will work there. You have to just do the design in right. So, yeah. Any other queries?
Any questions?
Obviously. So whenever we start the design, we always start from the ideal level. So you doesn't matter whether you do it in MATLAB or you do it in Verilog or you do it in Cadence directly using the ideal blocks. But you should always start with the ideal modeling, and then there you should get the exact performance which you have estimated. Maybe like there is already Shire toolbox is available for this delta sigma modulator design, so you can start with that, and then in your ideal model also the number should remain the same, and then you start one by one replacing these blocks to the real block. That's how generally a designer will do. Yeah. Obviously, yes, once GDS is ready, you can always send it for tape out. You have to just ensure that whatever you have designed is giving you the correct performance, because money is involved here, right? So you don't want to make a mistake. So that is the only thing you have to take care. Otherwise, the Cadence is the professional level tool which all the industry also use for designing their products. That's very straightforward. You can just type on YouTube generating GDS in Cadence. You will get a lot of videos. If you have a problem, you can drop an email.
say that. So this oversampling will take some time.
Obviously.
This will impact the response time of ADC.
So you can argue it in two ways. Like either you say that whatever is the allowable response time, my ADC has to work much faster. So that is the trade-off, obviously. So for example, let's say think about a audio bandwidth, right? So audio bandwidth is up to 32 kilohertz in a sense, but for most intelligent information, it is only up to 8 to 10K, right? So then your sampling rate becomes 20K. And now let's say if I use, like there are sigma delta ADC available which use only 1-bit quantization and operate somewhere around like 400 and 500 megahertz and can give you around 16 bits. So these solutions are there, right? So obviously now your ADC is running at much higher rate. Instead of 20K, you are running at 400 or 500 meg. But the benefit you are getting is your hardware is much simpler. You are just using a 1-bit ADC instead of using a 16-bit ADC. In fact, I have not talked about this, but let's say think about a flash ADC. So the flash ADC where you just keep on exponentially increasing the comparator, you get limited to let's say resolution of max 6 to 8 bits, because beyond that your mismatch among different comparators starts becoming problem. So the linearity of ADC becomes really tricky, and even if you have so many comparator driving all together same by the input is also a challenge. Like your input capacitance will keep on increasing. So things starts becoming challenging for conventional architecture, while this oversampled architecture seems much simpler in that way. The only trade-off you do is you operate them at much higher speed. But nowadays your process are pretty fast. Like even if I take an inverter, I can easily operate it at gig, so I need not to worry about it. So the speed is something which technology has given you. So now the only thing is how do you utilize that. So that's not a challenge. In fact, there was a time when people used to think that only for audio signals this CPDSM or DSM basically makes sense, because you need to do a lot of oversampling. But nowadays, even for image application where actually bandwidth is in megahertz, or even for in fact my modulator also, which I showed you there, the bandwidth was 10 megahertz. In fact, later on we have realized two modulator bandwidth extending up to 60 megahertz. There are examples where people have even gone till 250 megahertz signal bandwidth. So your sampling rate is even higher, like maybe 6-7 gigahertz. So nowadays there are, and these designs are very power efficient. When you compare power, like there are parameters to compare these power, which are known as figure of merit, so which fairly compare. So they are very competitive. So it's not like these techniques are very promising. It's not like they are not promising.
We have just witnessed a truly enriching and insightful session by Professor Ankesh Jain, sir, where he provided a deep dive into the complexities of high-speed ADC design. His vast expertise and real-world experience have undoubtedly broadened our understanding of this crucial field. On the behalf of Department of Electronics and Instrumentation Engineering and this entire student body, we extend our sincerest gratitude to Professor Ankesh Jain, sir, for sharing his invaluable insights and inspiring us all today. I would like to request our HOD, sir, to greet our esteemed guest with a memento as a token of appreciation.
See, one thing I should appreciate, the way Dr. Ankesh Jain has explained the development of sigma delta modulator type of ADC. That is excellent. You cannot find the same explanation in any of the books. He has developed that what this particular ADC means and how the construction is there and how the various sub-circuits are required. So I congratulate. the way you have explained that thing. So on behalf of the Department of Electronics and Instrumentation, I am really thankful to Dr. Ankesh Jain. Thank you.
I want to add here, in fact, you can permit me to explain your background. Actually, Professor Ankesh Jain, he came to, his wife is our alumni. She passed in, I think, 2013-14 batch, right? And they came in last vacation in April, May, so something that. That time our vacation was going on. So I requested him to, sir, whenever you visit, since you belong to here, in-laws belongs to here, so whenever you come to, please inform us a couple of days before so that we can have some interactions with you. So he agreed, and he just informed us on 9th, I think, some 9th of this March, and we tried our best to organize this. Thank you very much, and we will also like to interact more on this VLSI side. Sir also have proposed that he has some vacancy for PhD.
So that like basically right now we are running several projects. In fact, recently you must have heard in the news that Government of India has started a national quantum mission. So in this national quantum mission, they basically selected 14 projects across India, and I am part of 2 of such projects, and we have several PhD positions. So I'm not sure how many of you are in like final year and maybe looking to pursue PhD right after this time. But anyway, like even in near future, whenever let's say you want to pursue higher studies, so our group will have vacancies. We are looking for candidates who would like to do higher studies. And in fact, I will tell you one thing. Like sometimes there is a dilemma, like whether you should go for a higher studies or whether you should go for job. So. I agree many of you will be going through that dilemma, and some of you may not be even having that dilemma. You will be sure short, I will be going for industry, right? That can also be there. In fact, when I did my graduation in 2007, that time, like when I sit for the placement, just after my interview, HR person called me and started interacting, and then one question came, are you interested in higher education? And my answer was no. And I was honest, like I'm not lying to you. I was completely honest. I was not even 1% interested in higher education, because my philosophy at that time was, in these 4 years, you learn whatever theoretical knowledge are needed, and the rest is there in the real world. You do things, you learn by doing it, and that's how life should go. So I said that, and then I joined this industry, Freescale Semiconductor, where I worked as an analog designer. For 2 years I worked there. In fact, these 2 years were very fruitful. Like I got 2 US patent during this time. I got a very handsome increment also. It was just an accident that one day the company decided to do a very interesting project. In that they put me also, and we felt that for this project we don't have sufficient background, and then we called one professor from IIT Madras to explain us some of the topics, and that is the time when I felt, oh, this person knows much more than me, and that's how I went to PhD. Like after that, I think within 5 months I was in IIT Madras doing my PhD. So I am telling you, like the decision sometimes doesn't come that easily, but now I can tell you that you can see after my PhD also there was a choice. I can go back to the industry, right? But now I am in academia, so that means there is something in academia which was not there in the industry. But I am not saying the industry doesn't offer you things, but sometimes the academia has much more flexibility, especially in our field. This field, the two runs very parallel. Like whatever kind of work industry is doing, similar work is happening in academia. And plus point is academia gives you a flexibility to decide what you want to work on. Like in fact, my whole PhD was on ADC design, which I still do, but now I have gone into several other domains. For example, now I also work on a block known as energy harvesters. So energy harvester is a concept where you harvest the energy from the ambient environment, convert them into electrical energy, and then the idea is, can you run your circuitry using that energy? So basically we are not taking any battery. Like our circuitry will just rely on the ambient environment, take energy from that and runs using that. So these are the concepts. Anyway, research can go in different direction, but the flexibility with this you can get only in academia. Industry, you have to work on what customer is paying you to do for, right? So anyway, you can decide on these things. I just wanted to highlight. We have several positions. So those of you who are interested at this time or in near future can always write to me. Thank you.
Thank you very much, sir. We hope you do frequently visit your in-laws, and and we also get some spare some time for your expert lectures. Thank you very much.
So can you share your email ID?